Operational amplifiers, or for short, op-amps, are circuit elements that were mainly used to do some analog operations or calculations, such as subtraction, addition, and so forth. And they turned out to be much more versatile, and there's many configurations that will do a lot more than just addition and subtraction. So in this video, I'll introduce you what operational amplifiers are, what circuit module or model we use to actually represent them in a circuit, and towards the end, I'll end with some general strategies for solving circuits containing such operational amplifiers. So let me get started by introducing the circuit symbol for an op-amp, and this is here is the circuit symbol. So the circuit symbol shows us that operational amplifiers have two inputs. One, we call it an inverting input, and the other one is non-inverting input. And then the reason behind the naming will become much more obvious when we start talking about the different configurations. But for now, the inverting input usually has a minus sign associated with it, and the voltage at the inverting input, we usually term it as Vn, which is V negative. The N is for negative. And we have a plus sign in here for the non-inverting, and we term the voltage at that particular input as Vp or V positive. And we have one output out of this op-amp, which is just V out or V naught. Now, there's a couple of things in here that I'm showing you, and many circuit diagrams might not show them, but they're implied. And these are actually power supplies, or power, not necessarily power supplies, because you have to connect them to power supplies. So these are devices that are active. They need power to operate. So in a lot of circuit diagrams, you will not see them connected, but it is implied that you need to provide power for them to actually operate. And these are typically VCC and VEE, and depending on the circuit configuration or how you want to operate this op-amp, these are typically called the positive power rail and the negative power rail. So this would be the positive power rail, this will be the negative power rail. And depending on the circuit, you might want to produce maybe plus 12 volts in here and negative 12 volts in here. And some other circuits you might have like 12 and 0, depending on what you're trying to do. And in the case where you want plus and minus negative, what we do is typically we connect it with some sort of a power supply in here. For example, this will be the 12 volts, okay? And this one here will also connect it to the 12 volts. And what we do in order for us to actually guarantee that the bottom one would be negative volts is we connect the ground in here. So assume that our ground is somewhere in the middle in here. So the ground won't be connected to the VCC or the VEE. And this way we get a positive power supply that's plus and a negative power supply of negative 12. Now, in certain configuration where you actually want the negative power supply to be 0, all you have to do is just basically connect it to that 0. So what you do is you say this one is here, and that will be connected to the ground, and that will give you 12 and 0. So depending on the operation of the operational amplifier or what you want to do, you'll basically provide one of these two power configuration. But to work, like most of the circuits that I will show you throughout this module will not show you these power supplies, though you have to keep in mind that they're actually implicitly connected. Alright, so this is how an operational amplifier is represented in circuits, but what's actually inside it? Well, there are different implementations and different manufacturers for these operational amplifiers depending on the application you're trying to use them. So in here I'm showing you an example of one of them, and I believe this is the LF411N operational amplifiers. And if you're watching this video or you're following the circuits course that is part of this video or this video is part of, chances are you don't know most of these devices in here because you're just starting. So these devices, I'll show you just a few examples in here. For example, we have transistors, we have resistors, we have capacitors, we have diodes in here, we have Zener diodes, and it is much more complicated. It's very complicated. However, for purposes of circuit analysis, we really don't care about what's the internal configuration of this op-amps. What we're going to try to do is abstract all of these and just say, well, we have a positive input and we have a negative input somewhere. Probably here, well, this is the positive input, this is the negative input, this is the VCC, this is the VEE, and this is the V output. So we just summarize it with this particular symbol, and that's it. We just go on from there. So, but what we can do is we can, not only can we do this, but we can actually model it with a circuit model. So the circuit model that represents this much more complicated circuit is the following. So here's the op-amp, here's the negative input, here's the positive input, and as it turns out that we have a resistor at the input, and this is why we call it RI, because it's the input resistance. Okay, and this is just a resistor that is connected between the negative and the positive terminals of the operational amplifiers. And similarly, at the output, we will have an R output or an output resistance, and that's basically R naught. And also, this is the main thing. That's why we call it an amplifier. As it turns out, that it's just simply a dependent current source, or a dependent voltage source. So it's a dependent voltage source that depends on VD, and VD is just simply here, which is the difference between the positive and the negative. So positive with the positive, negative with the negative. So it's just simply VP minus VN. So let me just write this here. So the V difference is just simply the positive minus the negative edge. Okay. Just remember these VP and VN are in terms of ground. So Vn, this will be the positive, this will be the negative, and the Vn, this will be the positive, this will be the negative. Similarly with the V output, this will be the positive, this will be the negative. So as it turns out, the operational amplifier is simply a couple of resistors, an input and output resistance, and just a voltage controlled voltage source, and that's pretty much it. So we can model any circuit that contains it using just that simple. So instead of just using all of this complicated circuit diagram, what we can do is just use that. And I'll show you later that you really don't need the R input and the R output either. So you don't really need to do that, but we'll get to that shortly. Okay, so let me now connect some sort of a circuit to this input of the operational amplifier. So here's an operational amplifier, and again, I'm not showing you the power, but they're connected, and this is typical in circuit diagrams. Okay, so we have the op amp, and what I did is I connected some sort of a circuit, but instead of connecting a complicated circuit, I connected its Thevenin equivalent. As a reminder, a Thevenin equivalent circuit is just simply a voltage source and a resistance that represent a much more complicated circuit. And I've connected the positive of the V Thevenin to the positive and the negative to the negative just to make things a little bit easier. And similarly, at the output, what I did is I connected a load resistance. Okay, so that's basically how I will explain how an operational amplifier works. But since this is actually the circuit model, which is the R input and the AVD and what I did is now I just basically replaced the operational amplifier with its circuit symbol, just so that things are a little bit easier. And now what I really want to do is I want to write the V output in terms of the V Thevenin, or the input resistance. That's what I want. I'm interested to know, how does the output voltage relate to the actual V Thevenin, or the input voltage that I provided in here. So this is the voltage that I provided to the input. What does the V output look like? And that's what I'm going to do now. Okay, so let's get started. Well, simply, we'll start with the V out. Well, actually, these two resistors are connected in series, and I'm interested in the voltage across RL, and I know the source voltage, so all I have to do is just apply voltage division. So technically, V output is just simply the voltage across the RL divided by RL plus R output, the output resistance, times the voltage source is actually just AVD. By the way, this A in here is what we call the open loop gain, because there's no loop. If you see about it, there's no loop that comes from the output to the input, and later on we'll see something we call the closed loop. So this is just called an open loop gain. It's just a gain. Okay, its unit is usually V by V. It's unitless. Okay, or V divided by V. All right, so that's in terms of the V output, but wait a minute, what is the VD? Well, if you take a look at the circuit in here, that's where the VD is, and the VD is similar to what we just did. It's a couple of resistors connected in series, and I know the voltage source across them, and I'm interested in the VD, and VD is actually in the same polarity as the V Thevenin, so it's straightforward, there's no negative sign in here. So what I can say is the VD is simply the R input divided by R input plus R Thevenin. Okay, and that's basically V Thevenin in here. So now what I will do is I'll take that VD and just substitute it in here. Okay, that's here. It tells me V output is just simply RL divided by RL plus R naught times R input divided by R input plus R Thevenin times V Thevenin. So this is how the input is related to the output voltage. So there's a bunch of resistors here, and that's basically what typically we call the gain. All right, so this looks a little bit more complicated than it is, but it really isn't, and we try usually to simplify things when we talk about operational amplifiers. So with operational amplifiers, in reality, they do have an output resistance and an input resistance. But in circuit analysis, just to simplify things so that we don't get these gains and we don't have to remember such complicated equations, and I think I missed the A in here. This should be AVD because this is here. Okay, so in order for us to do these things, what we do is we'll do a couple of assumptions. We're gonna deal with what we call ideal operational amplifiers, and in ideal operational amplifiers, we define R not to actually tend to infinity or I input, so the input resistance will be very, very large, and it tends to infinity, and the R output would actually tend to 0. Okay, so we'll say that the output resistance is very, very small, and it tends to 0. Okay, and also in ideal amplifiers, we also say that the gain is infinity, but for now, we're just gonna ignore this particular assumption. Just let's focus on these two assumptions in here, which is the input resistance is infinity and the output resistance is 0. How would that affect this equation? Well, let's take a look. So if our input actually goes to infinity, so this goes to infinity and this goes to infinity. So these two, if you remember your math and limits, you will see that the R input will grow much faster than R Thevenin. So this term in here will become just simply, it just tends to 1. So I can just substitute this here by 1. That's all. All right, and in here, what we have is we decided that our output should be 0. So this will actually be 0. If this goes to 0, RL divided by RL, it also becomes 1 in here. So we end up with this particular equation, which is the V output is just simply A times V Thevenin. Okay, so what we did is basically it's just an amplifier. So an ideal operational amplifier is you provide an input voltage. It just gives you an expanded or an amplified version of it, dependent. Well, an amplified will depend on the value of A. A can be, well, A typically is a very large positive number, but in general, it just basically amplifies, and that's what an operational amplifier does. Okay. Okay, so let me summarize what I have done so far. So what I have done so far is I defined what an operational amplifier symbol looked like, and then I decided let's deal with ideal operational amplifiers when we do circuit analysis. It's just because it's simpler. So the ideal told me a couple of things. The R input, it will be 0, and the R input will be infinity, sorry, and the R input will be 0, basically. This becomes a wire, this becomes an open circuit. So let's make sure that we understand the effect or the influence of having that. So because we have the R input to be 0, so R input tends to infinity, what we have is we have no resistance in here. So effectively, if you think about it, what would be if I define this here to be my I negative, and this one here is to be my current with the I positive. So these here will tell me that the I negative is the same as the I positive, and both of them are 0 amps. So there's actually no current going through them. So let me just highlight this because this is one of the things that will help us analyze circuits. Okay, so IN and IP are typically 0. So there's no current going into the terminals of the operational of an ideal operational amplifiers. In real life, there will be some resistance that are super small, but for circuit analysis purposes, we're just going to assume that IN and IP both are 0. There's no current going into it. Okay, and what about, well, what's happening with our output to be 0? Well, if our output to be 0, that means it doesn't have an effect. No. Let me just now talk a little bit about the other assumption. The other assumption that the A, which is the open loop gain, it will basically be very large, and I'm going to just assume that it's infinity. So I have briefly ignored it, so let me just see what effect will it have right now. So if I take a look at that, I will know that the V output in this particular case is just simply A times VD. That's based on the assumption that the output resistance is 0, and the output voltage will become just simply the value of the dependent source in here, the dependent voltage source. Okay, but what is VD? Well, VD is somewhere in here, and it's simply VP minus VN. So let me just substitute that. So that will be A times VP minus Vn, positive minus negative, and that will be the V output. All right, so now if I just do a little bit of algebra, I'll know that Vp minus Vn is just simply V output divided by A. But we said that A actually tends to infinity, so that means the whole term in here actually goes to 0. If the open gain that we have is very large, the whole thing tends to 0. So I can just say Vp minus Vn is simply 0. That means Vp equals Vn. All right, so let me just go back to this circuit. So in reality, we say there's no resistance in here, okay? And that told me that the current going into it is 0 and the current going in here is 0. And at the same time, because the open loop gain, okay, the open loop gain is infinity, that means we can treat these here as if they're virtually shorted, and the Vn and the Vp will be equivalent as well. So this is the other thing that we're going to be using, and these two assumptions in here will help us analyze any circuit that contains an operational amplifier, regardless of what the operational amplifier it is. If we assume that it's ideal, it will give us these two things in here. Okay, now let's take a look at a real operational amplifier in the real world. Let me take a look at the data sheet of one of these operational amplifiers. So in here, I'm showing you the data sheet of the LF411 and LF411A actually. These are just one of the implementations of operational amplifier, and this is the data sheet that provides all the information about it. There's a ton of information. I'll just focus on a few things in here, and you can skim through it. So the first one is it tells me the chip basically pin out. So this is a chip that has 8 pins, and it tells me that pin 2 is connected to the inverting input, pin 3 is connected to the non-inverting input, and the output is connected to pin 6, and the V plus and V minus, these are the positive rail, and the negative rails are a pin 7, 4. And there's a couple of other pins with balance, which is beyond the scope of what I wanted to cover, and pin 8 is just simply not connected. So what I'm interested in is a few tables in here. For example, the table on page 5 in here. So this table shows me a lot of information. For example, it shows me the input resistance. So the input resistance at when it was tested under 25 Celsius, which is pretty common room temperature, it is 10 to the power 12. Well, we assume that the input resistance is infinity in an ideal amplifier. In real amplifier, we'll see it's not infinity, but it's extremely large. It's 10 to the power 12 ohms. And similarly, you'll see that what I called an open loop gain, and this here it calls it large signal voltage gain. For purpose of if you study electronics, this is something that is commonly used. But anyway, what's important is the following. It tells me that the typical value is 200, but this is volt divided by millivolt. Okay, so you have to convert the millivolt to volt, and you will see it becomes 200 times 10 to the power 3, which is 200,000. That's basically the gain, which is very, very large. It's not infinity, but it's very large. Okay, and it tells me that the minimum will be 50,000, and the typical will be 200,000. Okay, depending on the temperature. And it also gives me a bunch of other information. For example, we can go to, I believe, page 9. So in page 9, what I want you to see this here is the output impedance, and impedance is you can think about it as resistance, but in non-DC, basically AC currents or AC voltages. So you will see that the actual largest value is around here, and let's say that this is basically between the 110. This is basically 50 ohms, which is very, very small, even at very large frequencies, at 1 megahertz. In 0 in here, which is the DC, you'll see it's very, very small. All of them are pretty much, this is here is around the 1 ohm, maybe a little bit less, a little bit more. It's very, very small. And the rest of the data sheet shows you a lot of other information. For example, this is where I got the detailed schematics I've showed you earlier, and there's a simplified version of it, and you will see a lot of other information and how you can use it in other circuits and what you can connect it with. But the idea that I wanted to show is that the input resistance is very large, the output resistance is very small, and the gain is also very, very. So here are the key takeaways of this longish introduction to what operational amplifiers are. So operational amplifiers can be complicated, but we abstract all their internals and we just represent them with this particular symbol, which is have a couple of inputs and an inverting input and non-inverting input, and just a single output. They're connected to power, we just don't show them. And we will assume ideal operational amplifiers when we actually analyze a circuit, even though in real life they're not ideal. But if we do assume the ideal case, we have a few things that we can actually assume. So if it's an ideal case, that means the input resistance is 0. That means there's no current going into the negative or the positive terminals, or the inverting and non-inverting. So that's it. So IN and IP are exactly 0. And similarly, because we're dealing with ideal operational amplifiers that have an infinitely large gain, that will assume that there's a virtual short between the two terminals, even though there's no short. But basically, if you know the VP, you do know the VN, and vice versa. So once you take these two assumptions, and what you do is you apply nodal analysis. And in nodal analysis, you'll write a couple of nodal equations, or maybe more, depending on the circuit and how complicated it is. And you take a look, and what you really need to do is you need to express the output in terms of whatever is at the input. That's what you do. The output could be voltage or could be current, and the input could be voltage or current. You just have to basically write the output in terms of the input, and you'll be able to solve any circuit that contains such operational amplifiers.